Now we are going to discuss multivariable Variate Taylor series, which is a function from r raised to d to r. That means r dimensions, d dimensions to r, where that is moved at x0. When we define the difference vector delta is equal to x minus x0, the multivariate Taylor series f at x0 is defined as, it is just like your univariate series. Here we have one more term, f of x is equal to k equals 0 to infinity sigma k equals 0 to infinity dx k into f of x0 by k factorial into delta raised to k, where dx k f of x0 is the kth derivative of f with respect to x, evaluated at kth derivative of x. And Taylor polynomial is this one. That means Tn of x is equal to k equals 0 to n dx k f of x0 by k factorial into delta raised to k. We used slightly slopy notation of delta raised to k, which is not defined for vectors x element of r raised to d, where d greater than 1 and k greater than 1. And I will show you how this is done using an example. Taylor series expansion of a function with two variables. Consider the function f of xy is equal to x square plus 2xy plus y cube, and we want to compute the Taylor series expansion of f at x0 y0 is equal to 1 2. Okay, before we start, let us discuss what to expect. The function 161, this is the function, and that is a polynomial of degree 3. We are looking for a Taylor series expansion which itself is a linear combination of polynomials. Therefore, we do not expect the Taylor series expansion to contain terms of fourth or higher order to express a third order polynomial. This means that it should be sufficient to determine the first four terms of for an exact alternative representation. To determine the Taylor series expansion, we are going to find out f of 1 2 is equal to 13. That means we are putting x equal to 1 and y is equal to 2. We get f of 1 2 is equal to 13. Now, dou f by dou x, del f by del x, that means we are differentiating with respect to x. You get 2x plus 2y, and putting 1 and 2 there, we get del f by del x at 1 2 is 6. Del f divided by del y at 1 2 is 14. Therefore, we obtain d1 xy of f1 of f1 f2 is equal to f1 of 1 comma 2 is equal to del f by del x of 1 2 del f divided by del y of 1 2 is equal to 614. So that is the gradient. 614 is the gradient, such that d of 1 xy divided f of 1 2 by 1 factorial into delta is equal to 614 and x minus 1 and y minus 2, that is 6 into x minus 1 plus 14 into y minus 2. 14 into y minus 2. That means 614 is the gradient, and it is with respect to the point x equal to 1 and y is equal to 2. That means 614 into 614 is the gradient, and into x minus 1 y minus 2 is 6 into x minus 1 plus 14 into y minus 2. That is the first term. And the second term is, we are going to take the second order partial derivatives, del square by del x square, which is 2. That is, it's a constant. Del square of by del y square is equal to 6y. When we are putting the value 2 there, we get this 12. Del square of by del y del x and del square of by del x del y, both are 2, and we get the second order partial derivatives, and their values are 2 12 2 and 2. And when we collect the second order partial derivatives, we obtain this is the Hessian, h is equal to Hessian is del square f by del x square, del square f by del x del y, del square f by del y del x, and del square by y, del square f by del y square, which is 2, 2, 2 and 6y. Okay, this is a symmetric matrix such that h of 1, 2 is equal to 2, 2, 2, 12, and which is an element of r raised to 2 by 2. Therefore, the next term of the Taylor series expansion is given by del d square xy f of 1, 2 by 2 factorial del square is equal to 1 by 2. That means 2 factorial is 1 by 2 into x minus 1 into y minus 2, x minus 1 y minus 2 into 2, 2, 12, 2, 2, 2, 2, 12 into x minus 1 y minus 2. When you are expanding this, we get x minus 1 the whole square plus 2 into x minus 1 into y minus 2 plus 6 into y minus 2 the whole square. So d square xy f of 1, 2 del square contains only quadratic terms, second order polynomials, and then third order derivatives are obtained using this equation. And since most second order partial derivatives in the Hessian are constant, the only non-zero third order partial derivative is del cube f by del y cube is equal to 6 and del cube f by del y cube is equal to 6. High order derivatives and the mixed derivatives of degree 3 vanish such that d cube xy f of colon 1 is equal to this, and we get that is equal to y minus 2 the whole cube. So expanding this, we get an equation like this, and we will do more examples in the live session. Okay. So that's all about Taylor series expansion of multivariate variables, and we will discuss some examples in the class, and once you do those examples, will be thorough with these concepts. Okay, thank you.